very, very painful 10 minutes. So I just cut 10 minutes out of the YouTube video, and we're basically going to retake 10 minutes. But this is where we got to. We determined the gradient to be that, and we said that the gradient... let me get... Oh, no, I could have left that there. We said that the gradient would give us mu naught I over 2 pi r. And so we rearranged, and to 3 sig fig, we got exactly the accepted value. It was 1.26 by 10 to the negative 6. To 2 sig fig, it's 1.3. Now, here's where we're going to take it a step further. We looked at the error of the x values. It was a percentage error. So the greater the magnitude of the measurement, the greater the error. So the biggest one was the 20 plus or minus 2, going down to plus or minus 0.1. Now I don't believe you've added the error bars. So could you get over to this page? You did? Okay. And it turns out, oops, I didn't really pick a good scale step because my error bar has gone off the page. I'd probably lose a mark. And you all copied me as well, so you all probably would have lost a mark. So apologies there. So,
Do we need to plot error bar?
Absolutely. You are expected to. It'll be in the SIS test in term 3, and it may appear in the WACE because it has in the past. So in term 3, I've made up a booklet of error bar error analysis, and we'll spend a couple of lessons going through it. Yes?
Is it possible to have like error bars in both directions?
Absolutely. But it makes it much trickier.
Does it come like an error square?
It does. Yes. So you go from the top left to the bottom right. But we'll look at that in due course. Let's just look at a simple example. Now, gentlemen, I just picked this error, which is not the best because the top one, each little line is 2. So 0.2. And so the top error bar was 2, which is 10 lines. And then this error bar was 5, which was 2.5 lines. This error bar here was 2 lines, or 1.5, and then down here to half a line. So it's not the greatest, which is why I would also recommend you to use a sharpened pencil for your error bars. Now here's where we're going to go. If our error bars are if our data points have error bars, what we can find is a gradient maximum and a gradient minimum. And then from that, we could determine a mu naught maximum and nu naught minimum due to the uncertainty of our measurements of the x. So, here's where you're going to get your ruler out. And what we can do is we can make a maximum gradient that goes from the left of the bottom dot point up to the right of the bottom dot point to the top of the left dot point. Now you've got to try your darndest. And you've got to make sure that your line goes through each of the error bars. Okay? And this also allows you to exclude outliers. If there was an outlier where all of the error bars are within the line, the line is within all of the error bars bar one data point, you could choose to exclude that as an outlier, providing you have enough of the other data points. Now, we are going to give you most of the data will fall on that line. So again, you've got to make sure that it's touching the error bar on the Y value all the way across. And I'm pretty sure I've got that there. So I'm just going to get a thin, let's go a thin blue line, and we will just follow that from top to bottom of our graph. Okay? Now that is going to give a steeper gradient, but it falls within our allowed uncertainties. So our gradient could be as large as that blue line. We can then do the opposite. We could do the minimum. So we're going to go from the left error bar of the bottom to the right error bar of the top. And again, I would say that this dot point here at the 0.75, that's kind of restricting. I can't go all the way to the end of the top dot point, because if I was to, then this would be outside. But I'm going to choose to include him. So I'm going to get now a thin, let's go orange.
So does that not make it problematic then that there's y-intercept? Or is that
We're not going to worry about the y-intercept because we understand that there should be a 0. And obviously now, yes, we've got a positive and a negative y-intercept, but we're just using the gradient. Okay? So, here is the problem. Look at all this junk that we have. What I'm going to do, I'm going to cheat. Because I'm lazy, my two gradients intersect about there. So I'm going to use that as a common point number 1 for both my maximum and my minimum. So this is the tricky part, determining the x and y. So my x is 2, 4, 6, 8. Let's go 4.95, comma, and then my y is 0.25 below, which is 0.475. So times 10 to the blah blah blah. Okay. And then I'm going to try and find a nice... Now look, you're going to have triangles overlapping, and that's just an unfortunate thing, but you've just got to make sure that your working out is nice and clear. Okay? So I'm probably going to follow up this line here. And use this point here and that point there. So to try and make things a little bit simpler, my minimum and maximum, I'm just going to change my rise. I'm going to keep the same run for both my minimum and maximum gradient, and then I'm just going to extend my rise a little bit more for the maximum and a little bit less. That's just one way of making it a little bit simpler. Because our x coordinate is 14, comma, then we've got to go 1.25 plus 1, 2, 3. So that's 1.3 plus 0.75, 1.25 plus 0.75 is 325. Okay? So let's just, and again, you do the same because your lines might be slightly different. Again, it depends on your ability to draw your error bars and your ability to draw your lines of best fit. Your coordinate points might be slightly different. But I have enough here now that I can do gradient minimum equals y2 take y1. And this is where it becomes important now to write out your full working. So I'm going to put the general equation for the gradient, then I'm going to go about putting in my values. 1.325 take 0.475. It is all by 10 to the negative 5 over 14 take 4.95. Now remember, our gradient for the middle was 1.0 times 10 to the negative 5, I believe. So I'm expecting something a little bit less than 1.0. And this is where I absolutely majorly stuffed it up yesterday, and I'm going to right my wrongs. So I'm going to write it all out. I'm going to put a little bit more steps than is needed, just so I don't stuff it up. So 8.1 divided by 0.94. Please don't be so stupid. Yes. No. Yes. Negative 6. Okay. Well, we could, Tesla meters. If we just took the units of the y-axis, I'm happy for us to be a little bit lazy at this point. I would be asking you to expand out what a Tesla was, the kilogram per second squared per coulomb, but let's just leave it at that. Okay? So that agrees. It's slightly shallower, it's a slightly lower gradient, and so our mu naught minimum is going to be a multiple of that slightly lower gradient. Now I'm going to continue on and find the coordinates at the top. It's not too bad because we're sharing the same x value, but now I've got to figure out 1.50 take 0.25 is 1.475, I think. Yes? Times 10 to the negative 5. And now I'm going to, again, I'll use the blue text for my gradient maximum. So my y values are now going to change 1.475. Now, that's the only value that's different. It's comparing 1.475 to 1.325. So I can confidently just copy all of the other coordinate points from the working out above, because I have the same run. Oh, look at that. That's handy. That's just 1 times 10 to the negative 5 over, oh, do I risk it? Yeah, 0.905. Is that right?
9.05.
Yeah, 14 take 4 point. 9.05. Now, again, look, we're expecting our maximum gradient to be greater than that, and it will be. So it's going to be 1 divided by answer, 1.1 times 10 to the negative 6 Tesla meters. I don't know why I put that in brackets, but that'll do. Okay. So I'll quickly scribble that down, 0.94 and 1.1. Funnily enough, when I did this yesterday, I got the minimum as 0.96. Today I got 0.94. So just me drawing another line, slightly different, taking different coordinate points, my value was out by 2%. So again, there will always be a range for gradients. They will accept plus or minus about 5%. All right, so Excel will tell you it's this, and then we'll allow either plus or minus 5% generally for your inability to draw graphs. So let's take these two values. Back to page number, didn't have one because it's at the top, page 30. Now we have our equation up the top we're going to use, and we're simply going to enter the maximum. So mu naught max equals gradient maximum times 2 pi over current. And we said our maximum was 1.1. Which really, that's 10% larger, so I'm expecting a mu naught that's 10% larger. 2 pi on 5 equals 1.38 or 1.4. That should say maximum. And then our minimum was 0.94. Is 6% less. Divided by 5 gives 1.2. Cool. Now, here's the little trick. I've just separated this off. And hopefully you might have a little bit of paper at the bottom. You've got a range. And our absolute error, it's a little bit crude, but our absolute error is the range, or plus or minus, the range on 2. Yeah? So this is nice round numbers here. We're going from 1.2 to 1.4. That's a difference of 0.2. We divide it by 2. it's plus or minus 0.1, which is pretty, look, we went to 1.3 plus or minus 0.1. It agrees because we are at very low precision. We're only to 1 decimal place. If we had more decimal places, sometimes your range is, sometimes it's translated a bit. You might have noticed that our maximum was 10% larger, but our minimum was only 6% less. It's not always going to be equal. Depending on where your dot points are spread out and the sizes of the error bars, whether they are percentage, means that they get larger as the magnitude gets larger, or they might be an absolute, which means they stay the same width. And depending on where your data is spread along your linear graph, you might get the maximum is bigger or further than the minimum, and vice versa. Does that make sense? So that's why we have to do this little at the bottom. It is a little bit crude. So 1.4 take 1.2 over 2. Okay, question, Brownie?
What does plus range mean?
Oh, sorry, plus or minus. My bad. Plus or minus. So finally, the end point, we can then say we've determined mu naught to be 1.3 plus or minus 0.1 times 10 to the negative 6. And we got that from gradient max and minimum. Okay? But I thought just because we're a little bit ahead of schedule, and this will be coming up in term 3, I thought I would just show you at this point. And again, it's not the best because right at the start I just chose some stupid absolute error for my measurement of radius, which might not have agreed. As you saw, that tiny little error bars at the start. Okay? And again, because we have the time to do so, I thought we might go back. We did a graphical a gradient analysis of something else. I'm looking at these magnets and wires. If we can scroll back up to Padgett number, this one, 29, we were able to determine the magnetic field strength because the gradient was B times L. And we said that there was 2 centimeters in the field, and we worked out the gradient. Now, let's add some error bars. And I'll leave you guys to do it because I didn't plot the graph. Let's say we're plotting force, right? Look at this. We measured it on a scale that was to 1 decimal. Let's go. No, I want to make it nice. So our force... What was our forces ranging from 0 to what? What was our... 0.039. Could we just go plus or minus? And I'll give it just... Let's just say that the error is absolute, even though in this experiment it wouldn't be. It would be a percentage error. But let's say plus or minus 0.0... 0.005. Okay, and let's make that common all the way along. Okay, please and thank you. And so now we're going to have vertical error bars that have to go up and down 0.005 from the data. Apologies if you've gone... Yes, Louis?
You mean 0.005 or 0.0? Because our source value is 0.0049, 0.005, so it's 10 times bigger.
0.005. Yeah? Let's do it. Let's do it. See what... Worry about the concept... Huh?
How do we graph that though?
Okay.
It has to be within the...
Yeah, so maybe just not plot the bottom ones because it'll go off the page. So you're going to have your dot points, right? And they're all linear. And this is where your scale now becomes important because you have to figure out how many bars, how many lines.
It's not going to...
Okay. Can I look at your data, please? All right.
0.05 go off the page. Slightly.
0.05? Oh, what?
0.005.
It's bigger than the first point. Yeah, it's bigger than the last one.
Okay, yeah, sorry, my bad. 005, whoever asked me that. Okay, let's add more zeros. Sorry, I didn't realize the range of our forces was so small. 005. Okay, that's better. Nick, you're helpful. Can you just tell me your values, please?
Of force.
Yeah, from...
I went into 1 sig fig because of the table, so 0.0.
Yep.
0.005.
Yep.
0.007.
Yep.
0.009.
Yep.
0.01.
Yep.
0.02.
Yep.
0.03.
Yep.
And the bottom will be 0.04.
Oh, I get you. Okay. So, guys, this is where obviously you might wish to assign a magnitude on your y-axis, and then you would just plot from 0 to 4, because then you could go, I'm going to go 4 times 10 to the negative 2. That's how I would do it, rather than on your labeling your y-axis going 0.001, 0.002, 0.0. You just go 1, 2, 3, 4, and your axis heading has the magnitude. That's how I would approach this. Okay, so I'm going to plot these. So I'm going to be a little bit behind you, but I'm just going to take a photos of the data, and I will join you. Okay. Oh, what? Huh? So I'm going to go force bracket times 10 to the negative 2 newtons. 1, 2. What's up?
Just trying to get the units instead of Tesla meters, so to try and expand it.
Mm-hmm.
And I'm getting different values if you do it using this one and then the units which it gives you.
Yes, that's because if you were to add an amp there, it's coulomb per second squared, and the per second squared is cancelling out the kilogram meters per second squared.
So
They're cancelling. They're fighting with each other.
So I get meters negative 1 here, but meters here. So I'm really confused. So from up here you get, I use this one. Mm-hmm. So kilogram meters per second.
Hang on, let me check. Okay, so yes, we're happy with that, yes.
And then that's the gradient,
Which agrees, yes.
yeah.
All right.
And here, that's when you get.
So mu naught is
I've got meters up.
gradient over I, so we're going to take that and divide it by coulombs per second.
So the seconds cancel that, and then coulombs.
Yep, okay, yep, I agree with that.
And then, so if you do it that one, like how come the meters is on the bottom or on the top then? I have forgotten the meters there though. I should have written that down.
Do that. Gradient, yeah,
So I've got the
chuck it in
meters.
per meter. I'm not sure.
Oh no, I think I realised. It's because the bottom is meters, the gradient is meters negative 1. It's 1 on the meters.
Alright, so you just solved it. There you go. Cool. Let me get back to my plotting. Thank you. What are we plotting? F versus what? I. Alright, and we're going current up to 12. 2, 4, 6, 8, 10, 12. 1, 2. All right, Charlie, Cameron, Hal, Ben, plotting, please. All right, 1.3 to 5. 1.87 to
Errors are the same, that you don't get to set it here and then back. Would all the error bars be the same?
Yes. Yep, they'll all be the same number of cubes long, or lines long. It is substantial. 2.5. 3. That's not 2.5. 3.2. 5.3. Sorry?
I did it as 40. So I did times 10 to negative 3.
Yep. So now your error bars are 5 times 10 to the negative 3. Yes.
No, the 5 to the negative 2.
No? Okay.
No, they're 3, sorry. They're 3. My error bars are 5. Yes, you do.
11.45 goes to 4. That's 5 by 10, 1, 2. All right, so plus or minus 0.5. Holy moly, that's 10 lines. Wait, 10 lines? Yeah. All right. Again, this is what happens when Mr. Murray just makes up values, but now this is a good exercise because I chose measurements that were very imprecise, and so we should get gradients that are very imprecise. All right. So, is that what we got it looking like? Sweet as. Okay. So it's the same. We got. What did we get? Just out of interest, Patricios, you gave me the data. Could you tell me what the gradient was? From last week when we did this.
0.0036.
All right, cool. Thank you. And that's newtons per amp. All right. Come on, guys. Are we working? This is good experience.
So yeah, you just have to think about it.
Or you could choose to ignore that last data point because we did round it to to 0 decimals. No. Well, it might have. Patricios was a bit savage with his rounding, so rather 0.04. If we redid it. Actually, it's not 2 off. 4 times 9.8 is 3.92. So we're only going to shift it down by 2 lines. So I might actually.
Isn't it supposed to be 1 sig fig anyway?
3.9 is... I know. Oh, the last one.
The last one sort of just goes on the page.
Alright, so now minimum looks like... Now, okay guys, just have a look at the screen for me. I've just gone from the top of the first data point to the bottom of the last, and all the others lie within it. So that was nice. You don't have to be looking at every single error bar. You can just look at the first and last. So conveniently, I can just go from start to finish. Okay. And then if I now go the other way, if I just go from the bottom of the first to the top of the last, again, all the other error bars lie within. So I don't even have to worry about it. I'll go back to a blue now, or let's go yellow, green. No, oh, that'll do, whatever. It's the same damn colour. Now, have a look. You would notice that the maximum and minimum gradients are much more spread apart. They're much more different. And that is because I chose a very large uncertainty. You can see the size of those error bars on the graph are huge. And so, of course, that's going to allow our maximum gradient to be much larger and our minimum gradient to be much lower. So this experiment, we might say that it is accurate, but it is imprecise. When we get to the very end and we figure out a magnetic field strength, it's going to be plus or minus quite a large amount. So, I'll just quietly chug away. Again, if you want to be lazy, you could pick the point where they intersect. And then I might decide to go up this line here. 4.8. 2 below each one. That is 1.9. Are we working? What are you doing? You finished? Oh my god. Do you have any other work you could be doing?
Last minute Chinese.
Go for it. Not even mad. Not even mad.
Yes.
I'm not crazy.
All right, Y2. 3.55 take 1.9. Whoa, that's... Have I stuffed up? Have I stuffed up? It's got to be bigger than... Are you... Not that I don't trust you, but it's going to be what? It's going to be 4 over 12. No, it's going to be 0.004 divided by 12. 33. You lied to me, Trikios. You dogged me. I'm just taking the top dot point to the, Oh, yeah, no, that's right. 3.33. So, 165 divided by 100. Oh no, I'm getting 3.18. I've made an error somewhere and I need to find it. Oh, it's 5.8. Ah, there we go. That value there is not 4.8, it's 5.8. Oopsies, so that changes that to 5.8, which changes that to 4.2. Try again. 3.93. Phew. Cool. Happy? Yes. So again, if you're lazy and make one triangle for both, then you're only changing 1 point, and so we're changing the maximum to 2.95. Take 1.9.
Is F equal to Q?
What is that? That's 1.05. Two five. Well, hang on. It depends where you pick your points. It depends where you pick your x2. Well. So what did we say? Gradient equals BL. Therefore, B equals gradient. Oops. Divided by L. So each of those we're going to divide by 0.02. So divide by 0.02 equals, and divide by 0.02. Guys, are we doing this all the way to the end? People seem to have stopped. I got 195 millitesla and 125 millitesla. Uh-oh. So now, Patricios, did we say that the average was 160? Do you remember what you worked it out to be last week? The strength of the magnet, B equals? Oh, that's okay. I can do it myself at the top. Hang on. Divide by 0.02. $165. All right. So I got. Original, it was 165. The maximum gradient allows for 195, and the minimum gradient allows for 125. So our absolute error is going to be the range on half, plus or minus. So what's that? That's 70 on 2, plus or minus 35 millitesla. So we can now say that B equals 165 plus or minus 35 millitesla. And conveniently, the error is expressed correctly. Remember, the same decimal place as the measurement. All right, so that's as far as we can get with our working scientifically. All right, so that's why in year 11, we start off with the rules of adding, subtracting, multiplying, dividing, combining uncertainties, expressing your error. This is obviously going one step further. Yes, Robert?
Is this stuff being the exam?
Not the mid-year, but it'll be in the SIS test in term 3, and you can expect it in our exam or the WACE exam. Okay? How much time we got left? 5 minutes. All right. If the Chinese test students wish to depart, itadakimasu. Itadakimasu. Nicholas.
That's what he says.